Thank you very much for the introduction. I'd like to thank the organizers for inviting me here. The topic today is regulators of elliptic curves. I'll divide the talk into 4 parts, which gives me about 7 minutes per part. So try to pace. I start with the case of number fields. I'm going to give you a few facts about regulators of number fields in order to motivate what we'd like, what we proved and what we'd like to have over for elliptic curves over number fields. Okay. So the first part was number fields. Second part will be the result we got for elliptic curves over number field. Third part will be ideas of the proof, and the fourth part is another approach that I'll detail towards the end. So let me start. With this, so go straight to the theorem. So this theorem is a combined theorem, combined statement of 2 results. And it's combined from Silverman 84 and Friedman 89. And it goes like this, so let K be a number field. We're going to denote the discriminant of that field delta K. Its degree little d. Its regulator Rk, and its rank of units little rk. Then I define R0 to be the relative rank of, well, it will help me define the relative rank of units. So it's the max of Rf. The notation is the same as this one. So the rank of units of f being a strict number field inside K. Okay? So we have all the players in the field. Then we have 2 inequalities. So the first one is the regulator is bounded from below by the following expression. Delta K over d to the d to the power Rk minus R0. So that's the first inequality we have. The regulator is controlled from below by an expression involving log of the discriminant. You divide by the degree exponential in an exponential form, here as well, outside of the log. The power here is Rk minus R0, and C0 is a universal constant that is positive. So I'll C0 positive universal. So that's the first one, and the second one is another bound on the regulator of a slightly different nature. So this time I also have some universal constants, but I have the explicit form copied from their papers. And it goes like this. So that's the end of the statement. Okay, so the corollary now. The corollary is the following. So I'm interested in, imagine you have a family of number fields, and you want to understand if you bound the regulator from above. You ask that the regulator is bounded. You have a family. You want to understand if the family is in fact a finite family. So we're questioning if the Northcott property is valid or not. And so if you bound, so obviously you target Hermit's theorem. If you bound from above the discriminant, then you get finiteness. So we're almost there. So the thing is, if you bound this regulator from above, then you get a bound from above at this expression. You want to infer that delta will be bounded. Two problems. The degree plays against you. It's exponentially against you. And you also have the funny fact that maybe this power, which is always a non-negative integer, could be 0. So if it's 0, you don't get anything. So let's bound the regulator from above. So this, we've understood the problem, this. But we have a second inequality. And the second inequality tells you that if you bound this guy from above, the degree of the field is bounded from above as well. So this, using this, the fact that this degree is playing against you doesn't matter anymore. If this guy is bounded from above, these two are also bounded quantities. So the only thing you need to understand is this. But now we add in this little corner small proposition or lemma. Rk is R0 from time to time, but that's equivalent to K is a CM field. So a CM field is a totally imaginary extension of a totally real field. Okay, so if we know this, then we just exclude CM fields from the family. And what do we get? We get that there are, at most, finitely many non-CM fields, number fields. With bounded regulator. Yes, yes, it's even more precise. This corollary is slightly weaker, but I'm interested in that finiteness property. So, so that's the situation for number fields, and we'd like to understand what we can prove for elliptic curves defined over number fields. So. So, theorem. That's a joint work with Pascal Autissier and Marc Hindry. So what's the setting? So let E over K be an elliptic curve. Let me denote D, the degree of the number field, and let M be the Mordell-Weil rank of the group of rational points, which is finitely generated. Let me also denote H to be the height of the J invariant of the curve you consider. So E is defined over a number field, so this This J invariant is an algebraic number, and this H is the Weil height of algebraic numbers. All right, so then there is a real number depending on the degree and only on the degree of the base field, a positive number, such that the regulator of the elliptic curve over K is bounded from below by the following expression. And that's the end of the statement. All right, so so what's happening here? So you see this inequality is somehow I mean it gives information about the. I mean, imagine you have your elliptic curve given with a model, an equation, and you try to understand where are the rational points, where are the solutions. This tells you, this measures the volume spanned by the generators of your Mordell-Weil group. So the volume has to grow with the size of the equation. That's what it says. That's the kind of information you get from the inequality in question. Okay. So regarding the finiteness property I'm interested in, so I want to look at a family of elliptic curves now defined over a number field, and to understand what happens if I bound the regulator from above. So if I bound the regulator from above, similarly to what was happening over in the number field case, I have a few things that play against me. So the rank is playing against me because it's exponentially decreasing, but the height is playing for me. And of course, we know that there are only finitely many elliptic curves with bounded height. So here, as we bound the height of the J invariant, there will be K-bar classes. So that's what we target. We try to bound, if we want to get finiteness, we try to bound the height from above. We're almost there, so the rank is playing against us, but we also have a problem with the power here. So the power could be negative. Okay, if the rank is 1, then suddenly the height plays against you as well. So we have to take that into account in formulating the corollary. So that's what I'm going to do now. There are at most finitely many classes of elliptic curves over K-bar. So defined over K, such that the regulator and the rank are bounded from above with the extra condition that the rank M should be bigger than 4 in your family. So to prove the corollary, you bound the regulator from above, so now you have a bound. We ask that the rank is bounded, so then it's not in your way. Then you have a bound from above on this increasing expression, increasing as soon as the rank is bigger or equal to 4. So of course this term is the main term as soon as M is strictly bigger than 4. And if M is 4, it disappears, but we still have a smaller quantity that goes to infinity with H because we have a positive power here. So that extends the result here to families also if you include rank 4. Okay. So the reason why we're asking for the rank to be bounded from above, and we were not asking this in the number field case, comes from the fact that we have a second inequality over there that was doing the job for us. So this is the statement of the theorem, and I'd like to ask a question here. So if you want, this is 1 for the elliptic side, and 2 for the elliptic side would be, is it true that the regulator of an elliptic curve is somehow bounded from below by the rank? And yeah, the rank of the elliptic curve over K. So you can even be you can even allow any increasing function of the rank. You take log m, it will play the same role in this corollary, because it will just bound the rank from above as soon as the regulator is bounded from above. So that's a question. I don't know the answer, but I would be very interested in getting some information on this. Okay, so I'm going to give you some ideas about how to prove this. So basically, yes, yes. So in fact, if you take a closer look, the quantity we have here depends only on the degree. So you can even just ask here that the curve are defined over number fields of bounded degree. And in the question, similarly, you can just ask that the degree is bounded, because that's enough for the other one. But, Go again, please.
Do you expect the answer to your question to be positive?
Yes, but it's hard. Yeah.
Doesn't follow from some conjecture.
I'll say a word about this on the last board. Yeah. So idea of proof. So there's a key lemma. It starts like this. So you pick an elliptic curve over K. Defined over a number field, K. Assume that the rank is larger than 1. Well, I mean, if you want to study the regulator, assuming the rank is larger than 1 is obvious. Right, so it's not a restriction. So you assume this, and then assume as well that the number of rational point modulo torsion and with bounded height. So this is the Néron-Tate height as also, it's also the one that we use to define the regulator. So assume that the small points, modulo torsion, are controlled. So H and C, they are positive real numbers that are parameters. Then you assume that you have a control on the number of small points. Then the regulator of E is bounded from below by the following expression. And that's the end of the statement. So basically what's happening here is if you know how to count small points, you get information about the regulator. So this is just a principle, general principle of Euclidean geometry, right? You have this will form in the tensor of that set by R. You have a Euclidean space, and that's the quadratic form. And then you take a convex compact set, and then you want to understand if the volume, if you have a lot of points inside, what does it imply about the volume? So that's a measure of the volume, and that's something you get from Blichtfeld principle, essentially. So that's the key lemma. And then when you have that lemma, you transferred the problem of getting a lower bound into a problem of counting small points. So, basically, if you don't know what to do during the end of the talk, counting small points is always a good idea. It always gives something nice in the end. So basically, we now asked about how can we count small points in the most effective way so that H is big and C is small, and that will play for us. So Sinou David in '97, he gave the following counting result. So he has H is C1 V over D, and C is C2. So C1, C2 are universal positive, is DH, H V 1 plus log D over H. So what is HV? Essentially, this is the local height of the J invariant. Rho V, depending on what place you look at. You have this. But it's not so, it's not so important. You just go and take a look at his paper, and you realize that you have these quantities. Okay, so now the problem is this is not enough. It doesn't give you the inequality. So we looked around a little bit more, and then you also have a paper of Clayton Petch 10 years later. And he gives another counting result with different quantities. So height of delta E over K divided by sigma 2, and C now is C4 d sigma 2 log C4 d sigma 2. And here, so the height of delta, this is the log of the norm of the discriminant, the ideal discriminant of the curve. This is this H, so it's a different H, and sigma is the Spiro quotient. Which is the quotient of the log of the norm of the discriminant by the log of the norm of the conductor of the curve. So this counting result is not enough. This counting result is not enough. But if you combine the two and you optimize in various parameters, then you get this. You need to work for this, but the strategy is basically optimize in fact, in the number of bad places. Okay, so that's it for what I wanted to say about the proof. And I'd like to end with another approach. So there's a theorem I'd like to recall that's from Hindry and Silverman. 88. And it gives the following lower bound for any point P, the setting is the same, so any point P in the elliptic curve that is not a torsion point, then the height of P on E is bounded from below by a quantity depending on the degree of the field, and the spiral quotient times the height of E. So now the height of E here, put maybe height of E is max of 1 and Falting's height, if you want. So what you get as a corollary is then the following. The regulator of V over K by Minkowski's principle will be bounded from below by 1 over m to the m, and then this quantity, height of E to the power m. So this implies that you get finiteness of K classes of elliptic curves with bounded rank bounded regulator and bounded spiral quotient. So the two differences here. First of all, this deals with K classes because when you bound this from above, you get finiteness of K classes and not only K bar classes. Whereas in our theorem, we work with the J invariant. And secondly, here we need to bound the spiral quotient from above. So this is a lot to ask as well. So just to conclude, this is implied, this last term is implied by ABC. So if you have ABC, then you automatically have a stronger result than the one we proved. But what's nice here is that you don't assume ABC, of course. Okay. So I'll conclude here. Thank you.
So we've been asked to use the microphone for questions. So any of you has questions?
Okay, so in the Witz result over there, V can be chosen as we wish, or is it not important?
The place V?
Yes.
It's V can be chosen as we wish, and of course you make the best choice. So you take the one where the V-adic absolute value is the biggest one. Your Archimedean one in general, yeah.
Yeah, okay, sorry. For function fields, I guess the second approach means that the result works, right? And then you don't need m greater or equal than 4 because I see the exponent there, I see.
Yes, absolutely, you're right. So in the paper we also included, so this is the number field case, it's the harder. For function fields in characteristic P, you have a similar result, but you have to pay attention to inseparability degree in dealing with finiteness properties. And for function fields in characteristic 0, we also have a lower bound coming from that paper. So you can also say something, but you have to pay attention that you don't always get finiteness, say, over C of x. You have to take limited families. So there's you have to pay attention with how you formulate the finiteness property. But yes, it works for, you don't need m bigger than 4 in the function field case.
Yeah, go ahead and ask now, so I don't have to run back.
It's fine, I'll ask later.
Oh, there was a question over here. Yes.
Okay, thanks. Could you say something where the m minus 4 comes from? Does it come from one of the results you're citing?
So in this paper, so Sinou gives several results, and one of the results is a lower bound on the successive minima of the Néron-Tate height. And what he proves is that starting from m is 5, you have a lower bound on the successive minima that is increasing with the height. Okay, so then it means that if you input Sinou's work, you expect at least to have something with m being bigger than 5. It's not obvious, but you can get that. So m is 4 is harder to get, and m is 4 comes really from the optimization process. It's a bit hard to explain. I mean, it's basically computations, really. So, well, I can tell you that first we were. I mean, you need to optimize in fixing one parameters against the other. So, the parameter we use is the number of bad primes, and that's better than using the discriminant, for instance. It gives an improvement. That's how you get the log.
So have you tried to sort of play the same game with the optimization in the first two examples, with assuming that if you have unbounded Spiro quotient, then maybe one of David or Pesci's results is so spectacularly helpful for you that you get a more useful inequality?
I don't know. I mean, so Spiro plays always against you. So even if Spiro is unbounded, it will. I mean, the Spiro quotient in these inequalities is not helping. So I'm not sure that we can do it. Yeah.
Yes.
If I have understood correctly, you told that some conjectures might apply something regarding question 2. Yeah.
So I mean, what I'm saying is that if you have ABC, you have an inequality that in fact is stronger than inequality 1. So then you can try to use this to get something involving question 2. Imagine, for instance, that you can prove that the height is bigger than m to the power 1 plus epsilon. Then you're done. Because I mean, this is m to the m. This is m to the m. So if you have a little bit more than the rank, then you have something that grows. So that's the idea. So I mean, so it involves controlling the rank by the height to the power. So height bigger than m to the power 1 plus epsilon, or rank being controlled by the height to the power 1 minus epsilon. And for now, we have linear control.
Okay. Thank you.
It's not far, but.
Any more questions? If not, let's thank Fabien again.